So greetings of the day, students. So yesterday we have learned about processor registers and its capacity and functions. Today we are going to learn the common bus system, how the data has been written onto the bus and how the various registers will be able to read the data from the common bus. Let's see. So first of all, the basic computer has 8 registers, which we have did yesterday, a memory unit and a control unit. So paths must be provided to transfer information from one register to another and between memory and registers. The number of wires will be excessive if connections are made between the outputs of each register and the inputs of other registers. Let me explain this thing to you. For example, if register A is of 8 bits and register B again having the capacity of 8 bits, right? So I need to install minimum number of 8 wires, right? I have to connect each and every flip-flop with 8 wires. So the circuit becomes more complicated and complex when your number of bits increases. For example, if you have 64 bits of register, then you need to install how many cables? Minimum 64 cables, right? The outputs of register A will be connected to the inputs of register B. So this will create a choice. Okay. This will create a complex circuit. So this is not a possible solution. So the better solution is common bus system, right? So we will be using, if you have 16 bits of register, we will be using a 16 bit of common bus. A single bus will be used whose capacity is 16 bits, right? A common bus will be used between these two registers whose capacity is 16 bits. So this will reduce your circuit, this will reduce your wires. So ultimately the cost factor, right? If you want to install one single cable, that is cheaper as compared to installing 16 different cables. So this solution is cheaper solution as compared to the previous solution in which we have used the individual cables to each flip-flop. So that is the reason we have used the efficient technique which is called common bus system concept, right? So the registers in the basic computer are connected using a bus. This gives a savings in circuitry over the complete connection between the registers. So we have learned in the last lecture that how a common bus system will be established. We have discussed two techniques. The one is with the help of mux and the other is with the help of 3-state bus buffers, right? So these are the two techniques with the help of which we are going to develop the common bus system. We have learned it in last lecture, right? So how writing onto the common bus system is achieved? So first of all, You need to discuss 3 to 4 things whenever a common bus system will be covering. You will have to cover 3 to 4 things. The first thing is how a writing, is done onto the bus, right? Number 2, how the data reading is done from the bus. Number 3, when memory comes, how reading and writing of memory is achieved, right? We have to discuss these 3 things in the common bus system. Number 1 is how writing onto the common bus system is achieved. Number 2, how reading from the bus is achieved. Number 3, whenever a memory reads something or memory writes something, right? How it can be achieved, right? So let me show you the diagram first. So we have 2 diagrams for the same concept. So these are the registers which we have discussed yesterday. I hope you remember it. So we have a total number of 8 registers. AR stands for address register. It is of 12 bits. PC stands for program counter. It is of 12 bits. DR stands for data register. It is of 16 bits. AC accumulator, which is of 16 bits. Then we have INPR. It is of 8 bits and it stands for input output register. Then we have IR. IR is instruction register, which is again of 16 bits. Then we have TR. TR stands for temporary register. Again, it is of 16 bits. Last but not the least, we have outer register, again, which is of 8 bits, right? So 4 and 4, a total number of 8 registers are there, and a memory is there whose size is 4096 into 16. So let me complete the diagram. So this is your 16-bit common bus, right? This complete U shape is a 16-bit common bus system, right? So first of all, a memory is having read and write signals, right? So how at each register it is having 3 inputs. L stands for load, IN for increment, INR for increment, CLR for clear, right? So every register is having L, INR, CLR inputs, right? So similarly AC, but INPR does not have these 3 inputs, right? Because whenever you are pressing any key from your keyboard, the data will be sent to INPR register. INPR register stands for input register, and it receives the 8 bits of character from the input, right? Then we have IR, instruction register is also loaded only, right? Then TR register is having 3 inputs. So then we have out R, right? So these are the connections. AR register deals with the address, so that is why this is connected to the memory, right? Because whenever you are reading something from the memory or you are writing something onto the memory, you need one address where to read the data or where to write the data. For example, if you want to access the document from your C drive, then you need the location of where to find that particular document, right? Then these are the connections. Then we have adder and logic circuit. which is having 3 inputs, right? So S2, S1 and S node. So these are the selections line. I will
So
let
what is
you
the
know about the complete diagram in few minutes. So here you can see that one number is written along with each register and memory, right? You can see it. Right? So I will give you one more diagram, which is easier diagram as compared to the diagram which is in front of you. So it's up to you which diagram will be taken by you people. Whichever will be easier, you can draw that diagram in the examination, right? So this is the diagram for common bus system. So first of all, how writing onto the bus is achieved. How writing onto the bus is achieved. That is this concept. So as you all people can see that one number is written alongside the register. For example, in front of AR, one is written in front of PC, 2 is written in front of DR, 3 is written in front of AC, 4 is written and so on, right? So how writing will be achieved? For example, here you have S2, S1 and S node. These are the 3 selection lines. Whatever the number which is written alongside your register, for example, we have a calculator register and the number written is 4. So what is the binary value of 4? 1, 0, 0. So the binary value of 4 is 1, 0, 0. So it will be, these values will be loaded into S2, S1 and S node. S2, S1 and S node will become 1, 0, right? 1, 0. Then the contents of that particular register will be written over to the bus. Let's suppose this is your bus, right? So then this register will be writing the contents onto the bus by setting S2, S1, S node to 1, 0, right? I hope the concept is clear. Similarly, if PC wants to write something onto the bus, then the number written alongside PC is 2. So how you can write 2? It will be 0, 1, 0. Then the contents of PC instead of AC, it will be written onto the bus, common buses, right? So this concept is called writing. So registers. Now the concept is how the registers read the data which is written over the bus, right? So you can see that every register is having L input. Every register is having L input. L stands for load. So register will be reading the data by enabling the load input. By enabling the load input, particular register will be reading the data from the common bus system, right? So register whose load input enable that receives the data from the bus, right? So this is about the registers. Then the concept of memory is there, right? So whenever a memory whose size is your memory is of 4096 into 16 bits, right? Here you can see that one read is attached and one write is attached, and then address is connected to AR, and the number which is written along the memory is 7, right? If memory if memory wants to write something onto the bus, first of all, how writing is achieved? Writing is achieved with the help of selection lines. What will be the number? That is 7. So S2, S1 and S0 is having 111 as a value, right? So here you have 111. Here, which operation will be performed? The data is going outwards. It means reading is achieved. Memory reading is achieved. The data is going outside, which means memory read is performed, right? So you can put the data onto the common bus from the memory by enabling the read signal and setting 111 in S2, S1 and S2, right? So this is memory read operation. Now how memory write operation is achieved? Again, first of all, so let me discuss the concept of AR in few seconds. So how writing? So writing is achieved with the help of this input line and by activating the write signal of the memory unit. The 16 bits content will be written over the memory by activating the write signal. So how, which location you will be writing or which location you are going to read from the memory, that particular location will be given by address register, right? That particular address will be given by the AR. Otherwise, one extra wire will be used, which will be serving the purpose of address bus, right? Otherwise, you have to use one more bus, one more cable, which will be serving the purpose of address bus or address line. So to avoid it, we have used one register which is called AR register, right? So all the addresses will be handled by AR register, which is of 12 bits each, right? So this is the writing onto the common bus system. You can see the table for every register. So this is a decimal representation 0, 1, 2, 3, so on up to 7. Because 0 number is not assigned to any register, that is why I have put a don't care condition cross sign in first row, right? So how a writing onto the common bus system is achieved? It will be achieved with the help of 3 control lines, S2, S1 and S0, right? If any register wants to write some data, for example, accumulator wants to write some data onto the bus, so the number written along with the accumulator, its binary value will be given to S2, S1, S0. 100, it will be given to selection lines. Then the contents of that particular register will be sent onto the common bus system, right? Similarly, the contents of memory are placed using the read signal and the selection variables having the value 000 because its value decimal value is 7, right? And by enabling read input, the contents of memory will be placed onto the common bus system, right? So you can see the table which is given in front of you in the PPT, right? So next we have reading from the common bus system. So using the control input of the register, which is called load input. That is called control input, LD, right? So how a register reads the data from the common bus system with the help of by enabling the load control input. This is the input, right? And by reading the data from the 16-bit common bus into its flip-flops, right? Similarly, memory receives data using write signal. Memory receives data from the common bus using by enabling write signal. So either one of the registers will have its load signal activated or the memory will have its read signal activated and will determine where the data from the bus gets loaded. So here you can see that one mismatch occurs. So what is that mismatch? As you all know, AR and PC deals with 12 bits, right? Whereas TR, DR, accumulator and IR, it deals with 16 bits, right? INPR and OUTR deals with 8 bits, right? So you can see that we are using the concept of common bus system, which is of 16 bits. So what will be the remaining values? Where are those remaining 8 bits goes? Or in case of 12 bits, where are those 4 bits goes? So the concept is whenever AR register is going to write onto the bus, its 12 bits will be loaded onto the 16 bits by having most 4 significant bits to 0. This is called MSBs. These are your LSBs, least significant bits and most significant bits. It will be then it will keep the 4 most significant bits to 0 in case of AR and PC, and the remaining 12 bits will be written onto the common bus system. Similarly, whenever 8 bits of data will be received, INPR, which is taking the input from the keyboard, it receives only 8 bits, right? And the outer register is giving the output to the monitors to display the 8 bits of characters. The other 8 bits, most MSBs of 8 bits will be 0. Will be 0 in case of these two registers, right? So here you can see from the diagram that so you can draw either this diagram in the paper or one more diagram is there. So let me show you this diagram. So I think this diagram is a little bit easier as compared to the previous diagram, right? This one is the simpler diagram. right? So here you can see that the unit, arithmetic and logic unit receives the input from three different things. So basically accumulator is getting the input from number one DR, that is your data register, and the second input is coming from accumulator itself, and the third input is coming from INPR, right? The accumulator deals with three sets of input. The first is called DR, the second one is called accumulator itself, and third one is called INPR, right? Whenever you are going to perform arithmetic and logical operations, then DR and AC will be taking part. For example, add DR, right? So how this operation will be performed? You have to add the contents of accumulator with the contents of DR, and the data will be again stored to accumulator. How? Let me show you. So first of all, here the contents of DR will be loaded into the ALU, right? From this side, the contents of accumulator will be loaded from this side. Then the AND operation will be performed and the result will be stored back to the accumulator itself, right? So whenever you are going to press any key from your keyboard, the 8-bit characters will be stored into INPR, and which is sent to the ALU, right? If you want to perform add operation, add the contents of AC to DR. Let me perform this operation. Add. So here the contents of accumulator is 1001010 8 bits, and the contents of DR is 00110100, right? So now you have to perform the add operation. So 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0 with 1 carry, 1 plus 1 is 0 with 1 carry, 1 plus 1 is 0 with 1 carry, 1 plus 1 is 0 with 1 carry. So this is the result for your addition. So this one will be sent to E. E is your extended flip-flop. You can see in your diagram, and flip-flop is attached, right? So again, these contents will be stored into the accumulator itself. After performing the add operation, the extra, this is your carry, which will be sent to the extended flip-flop E, right? Or you can say it as AND carry. So for example, here we have to perform this operation. First operation is AC goes to DR, AC goes to DR, and the second one is DR goes to AC. So how it will be achieved? So first of all, let me show you the diagram. So here how the contents of AC will be placed onto the data register? First of all, the contents of AC, the number written alongside AC is 100. So S2, S1 and S0 is having 100. By enabling, by writing 100 in the selection lines, accumulator will be writing the data onto the bus. Suppose this is your common bus. After that, the DR register will be activating its load input and it will read the data from the common bus. With the help of this, the first operation will be achieved, right? And how the second operation will be achieved? The data register, see the diagram, by enabling the load input of accumulator, because this time accumulator wants to read the data from the DR. So simply by enabling the L load input of the accumulator, DR will be sending the data to the accumulator by enabling this L, right? So this is all about the common bus system.
सर आपका माइक म्यूट है.
So let me start with the basic computer instruction format. So first of all, yesterday we have learned about the instruction format. Instruction format. Your instruction is of 16 bits, right? And it is divided into operation code, your address, or it may be operand, or the ith bit, right? So as your memory is having a capacity of 4096 into 16, from this your instruction size is 16 bits. This is your instruction size or data bus size. And how you can write 4096 2 raised to power 12. So from here you can calculate the size of your address. So that is why we have written 0 to 11, bit 12 to 14, and this is your bit number 15, which will be denoted by I. So basic computer instruction format divided into 3 categories. The first one is called memory reference instructions. The second one is called register reference instructions. The third one is called input output instruction. So three main categories are register reference, memory reference, and input output reference instruction. So let me discuss. The first one is in memory reference instructions, your value of operation code, will vary from 000 to 110, right? Your operation code's value varies from 000 to 110. That is from 0 to 6. From 0 to 6. And in case of register reference instruction, your operation code will be 111, and the value of I is equals to 0. The operation code value is 111. 111 means 7, right? Next we have, in case of input output instructions, the operation code's value is 111, and the value of I is equal to 1, right? So let me show you with the help of this format. In case of memory reference instruction, the bits from 0 to 11 will be your address. It will be your address, and the bit 12, 13 and 14, will serve the purpose of OP code, and it will take these values 000 to 110, right? And for register reference instruction, instead of address, it will serve the purpose of register operation. Whereas the OP code value will be fixed. It will be 7. Because of this 111, right? And this I is equals to 0. And in case of input output reference instruction, the operation code's value is 111, and this is your input output operations, IO operation. So let me show you the table. So here you can see that your table is bifurcated into 3 parts. The first section 1, 2, 3, 4, 5, 6, 7. The first 7 instructions belong to the category of memory reference instructions, right? The another 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These 12 instructions belong to the category of register reference, and the below 5 belongs to the category of input output, right? So let me explain you how this XX0 will be written, right? So let me explain this. memory reference instruction. The operation code's value is 000211, right? So I already told you that the bits 0 to 11 will serve the purpose of address. So mark it as X, X, X. Mark it as X, X, X. That is how many digits are there in hexadecimal? 4. Right? A total 16 bits of hexadecimal address. It will be composed of a total 4444. Right? So I have denoted these 12 bits with X, X, X. Right? Now the bit number 12, bit number 13 and bit number 14. It will be vary from 000 to 110. It will vary from 000 to 110. Right? It will remain XXX throughout. Right? So it will give you 0 to 6 range. 0 to 6 range when the value of I is equals to 0, your operation code will vary from 0 to 6, right? When your value, when I is equals to 1, when the 15th bit will be 1, so when it will be 1, the value become 1000, that is 8. Right? When this bit will become 1, the value becomes E, 14. It becomes, this becomes 1110. 8, 4, 2, 1. 8 plus 4, 12 plus 2, 14. So this is your E. That is why the range written is 0 to E triple X. I hope the concept is clear, right? Let me explain it one more time. Because your instruction is of 16 bits, the bits from 0 to 11 will serve your address bits. Bit number 12, 13 and 14 and 15, because the instruction will be of 16 bits each. The bit number 12, 13 and 14, it will serve the purpose from 000 to 1, 1. Let me complete the entire range. So 000 से starting to 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0. So this is equivalent to 0 and this is equivalent to 6. 1 2 3 4 and 5. Right? When the 15th bit is 0 0 0 0 0 0 0 and 0, your range will vary from 0 to 6 when I is equals to 0. Right? It will be 0 to 6. Right? When the value of I is equals to 1, which bit represents I, that is our 15th bit. When 15th bit becomes 1, it will be 1 1 1 1 1 1 and 1. Now calculate their decimal values. 1000 is equals to 8. 1001 is equals to 9. 1001 is equals to 1010 is equals to A. 1011 is equals to B, C, D and E. That is the reason you can see in your table that the value varies from A to E. So these are your memory reference instruction, and add, LDA, STA, BUN, BSA, ISZ. We will discuss these instructions in detail in next lecture, right? What will AND is doing, LDA is doing, STA is doing, right? So let me move to the second section, that is register reference instructions. So here we have a total number of 12 instructions are there. The first instruction is CLA. How this 7 appears, 7800, how it appears. So in case of register reference instructions, what is the value of opcode? The value of opcode
7.
7. The binary equivalent of 7 is 111, and the value of I is equals to 0. It means 7 throughout 7. So it will be 1 1 1 1 1 1 1 1 1 and so on, and it is 0. So what is this value? This is equals to 7. This is equals to 7, and from bit 0 to 11 it represents your register operation. It can be any operation. So here it is 800. So in first case it is 7800, which is your CLA. In second case again it is 7. It is 7400. This 400 is a register operation, right? So that is the reason you can see in the table in each instruction 7 is written, 78, 74, 72, 71, 7080, 7040. I hope the concept is clear, right?
Yes, sir.
And in case of last column, which deals with input output reference instruction, in case of last reference input output reference instruction, the value of I becomes 1. The operation code's value is again 111, but the value of I is 1. So in this case 1111, what is this? This is your F. When you have 8421, if all the bits will be 1, this is equal to your F value, hexadecimal value F. So that is the reason you can see that in all your last instruction, that is INP, out, SKI, SKO, F is written alongside, and these 12 bits represents your IO operations. So here you can see that F800, F400, right? I hope the concept is clear now. Next topic is instruction set completeness. So instruction set is said to be complete if it includes the sufficient number of instructions in each of the following categories, right? It is said to be complete if it includes sufficient number of instructions in each of the following categories. Number 1, it is having arithmetic, logical and shift instructions. We have already discussed it in chapter number 4. Next, the instructions for moving information to and from memory and processor registers. right? For example, move A, or you can say that move B. Then we have program control instructions together with the instructions that check the status conditions. We will discuss it in chapter number 8. Next we have input and output instructions. That's it. So when all these 4 categories of instructions will be part of your set, then the instruction set is said to be complete, right? So next we have control unit. So control unit of a processor translates from machine instructions to the control signals for the microoperations that implement them. What is the purpose of control unit? It will give you control signals, right? So control unit is responsible for the generation of control signals. So control units are implemented in one of the 2 ways. The first one is called hardwired control, and the second category is called micro-programmed control unit. So in hardwired control, CU is made up of sequential and combinational circuits to generate the control signals. So in case of hardwired control, your CU, that is control unit, is made up of components such as sequential circuits or combinational circuits to generate the control signals, right? You need not to write any sort of programs in case of hardwired control. Everything will be in the form of hardware. Next we have micro-programmed control unit. A control memory on the processor contains micro-programs that activate the necessary control signals. So in case of micro-programmed CU, a small program will be written which will generate the control signals, right? So let me, this is your hardwired CU, and this is your micro program CU. So here components are required like gates, sequential circuits, combinational circuits, etc. Means various components will be used. That is why this is called hardwired control unit. But in case of microprogram control unit, there will be no such components. Only a program, microprogram will be written. Microprogram will be written which will generate the control signals. But in case of hardwired CU, these components will help to generate the control signals. A lot of cost is involved because hardware is costly. It is very much costly, so a lot of money. This one is the costly solution, and this one is the cheaper solution. If you want to make some changes in hardwire, you need to amend the entire circuit. You need to change the gates, you need to check the sequential circuit, you need to check the combinational circuit if any error occurs. But in case of microprogramming CU, you just need to change your program. Small efforts are required to change the microprogram, but a huge efforts are required to change the circuitry. So these are the main differences between hardwired and microprogrammed CU, right? Any doubt till this point? So in hardwired organization, control logic is implemented with gates, flip-flops, decoders, and other digital circuits. It has the advantage that it can be optimized to produce a fast mode of operation. But it requires changes in the wiring among various components if the design has to be modified or changed. You need to do a lot of changes in these components, right? So any doubt to any student?